The electric force is actually a billion times stronger than gravity. So if I were to have 1% extra electrons somehow in my body, and you also had 1% extra electrons in your body, if we were to stand a meter apart, I would repel you with a force strong enough to lift the whole Earth. So then why isn't electricity the dominant force in the universe? Why does it seem like gravity is a much bigger deal? Well, gravity is only attractive. So where you have mass, it attracts mass, and you tend to get more and more gravity. But when it comes to electricity, where you have positive charge, it attracts negative charge, and you get neutral. So most things are neutral. Like this metal door here. If I touch something that's metal and it doesn't shock me, I can usually assume it's neutral. It has an equal number of protons and electrons. So one thing that is kind of curious with electricity is if you charge an object, like this balloon, you can get a charged object to stick to a neutral object. Maybe. Might need a little more charge. There, it's stuck. So how do charged objects stick to neutral objects? Well, I have a drawing over on the board that I'm going to show you. Kind of explains this situation. I'm going to back up a little bit. So here's the balloon, and it was charged. It had all these extra electrons, so I'm going to draw them in right there. And it approaches the wall, this is the wall right here, which is neutral. Well, as it's approaching, the electrons in the wall don't like that balloon, and they're able to run away because it's a metal conductor, so it lets its electrons flow. And so they run kind of towards the back of the wall, leaving pretty much just positives here, or they might run down towards the bottom or up towards the top. But we get a region right here where we can have attraction because the charge is lined up. So the wall's still neutral, but it's polarized, which is a word that we've already talked about. Polarization is when charges line up. So polarization also is an important reason why we can get cloud-to-ground lightning. When you see thunderheads, cumulonimbus clouds, it's because there's really strong vertical winds kind of pushing moisture way up in the air. And so in the cloud, you'll kind of get these cycles where the moisture is being blown up and freezing and then falling back down and adding layers, and you're kind of building hailstones in that cloud. Well, as it goes to the top of the cloud, every time it's grabbing some electrons, which is something moisture's good at, and then dropping them off down here at the bottom of the cloud. So we're starting to get a pretty good charge difference between the bottom and the top of the cloud. Well, you might have the same thing going on in a nearby cloud. And so there's some attraction between this bottom of this cloud and the top of this cloud. And if the attraction is strong enough, we can get cloud-to-cloud lightning, which is something that's pretty common. And it takes 1,000,000 volts or more for it to make that kind of jump. It actually takes 10,000 volts for a spark to jump an inch. And we're jumping lots of inches. So there has to be a lot of attraction for it to jump through the air, because the air is a pretty good insulator, but it does, right? We see cloud-to-cloud lightning, and we also see cloud-to-ground lightning. The reason that we have cloud-to-ground lightning is because this tree, which is right underneath this cloud here, eventually starts to notice, hey, there's something really negative over me. And the electrons in the tree don't like that, so they start running to the roots of the tree and to the ground, leaving mostly positives up here in the top of the tree. And you may have actually experienced this before yourself when maybe you're out golfing on a day where it's starting to get kind of stormy out. All of a sudden the hair in the back of your neck starts to stand up. That's not a good place to be, because basically what happened is the cloud just pushed the electrons out of you to the ground. And now you're basically saying, pick me to the cloud. So if there's enough of an attraction, we can get sparks to jump from the cloud all the way to the ground and have cloud-to-ground lightning. And again, it's about 10,000 volts to jump an inch. So a good way to protect yourself from having your electrons leave and run to the ground is to be insulated from the ground. But it turns out that when it comes to being safe from a storm. A lot of people think that the main reason you're safe in a car is because of the rubber tires, but there's actually something else. There's a cage of metal around you. It's called a Faraday cage, which is the thing we're going to talk about next. Right, I have a Van de Graaff generator here, which was made in 1931. Well, this one wasn't, but the first one was, by Robert Van de Graaff, American guy. And what it does is it builds up a charge on this metal sphere. I think it's actually a positive charge, but it does it by having a belt, which is a rubber belt, so an insulator, take electrons from the sphere and bring them to the ground, which I suppose most good generators don't need to be plugged in, and this one is plugged in, so you could turn this with like a hamster or something, but the idea is that you're spinning this belt really fast, it's grabbing electrons, and you have a big area that you can grab them from. The bigger this area is, the more charge you can get built up. So this thing is actually able to build up enough charge difference that it can get several thousand volts. It takes 10,000 volts for a spark to jump an inch, and you can see that it's able to jump at least that far. That was about 3 inches. What I want to show you with it is what happens when you put an object next to it that is not grounded and an object that is grounded. So we'll get rid of all these extra charges here. I think everything's pretty much been discharged to neutral now. So I have the two pom-poms about equal distance from the generator, and you can see that one of them I've ran lead to the gas supply so that I know it's grounded for sure. And the other side has this nice plastic insulated base, and it's not connected to the ground. So I just want you to see the effects of this on the grounded versus the not grounded. You can see it's having some impact on the one on this side, but much more on the side that's grounded. All right, the other thing that we talked about was, I'm gonna have them both be non-grounded now. What about this cage of metal idea? So this was something discovered by Michael Faraday, which is called a Faraday cage. And what Faraday said is that since charges want to repel each other, they want to get as far apart as possible. So if electricity, a bunch of electrons are flowing, they're going to flow around the outside of a conductor as much as possible and not at all around the inside. So if you're inside of a cage of metal, you're going to be completely shielded from any electric fields on the outside. And you can see that when I turn this on. Again, the one on this side is having a big effect from Van de Graaff, and the one inside the cage is not having any effect at all. Even if it were to touch the inside of the cage, it's completely protected, while some of these tassels on the outside are being affected by it.